working? Yes, it's working. So good afternoon to everyone. I hope that you have a nice lunch. So we're going to start this session, which is about the INSAR data products and services. So we have 4 or 5 presentations. I don't remember. All the speakers are there. So I think that we can start with the first presentation that will be given by is it Florian Provost from the University of Strasbourg, that will talk about the timesat service. Oh, sorry, and I forget to present myself. I'm Nuno Miranda from the European Space Agency, and my co-chair,
José Manuel Recado Blasco from REA Group.
Thank you very much. So my name is Florian Provost. I'm going to present you the service called timesat, which is a service that aims at classifying large data sets of ground motion. So to start with some context, so there are currently more and more very large data set of ground motion products, such as the AGMS, but also nationwide processing that are done with different processing chain. And you have them in interferometry, but also with image correlation, such as the ETS Live that is monitoring globally the glacier. So those very large data sets present different challenges to exploit them and understand what they really contain and what are the relevant inside them. So to do that, we need to develop new tools to get rapid analysis and use HPC or cloud processing to do that. So for timesat, so we were specifically interested on monitoring landslides. So this service was developed within the project, which was called EO4 Alps landslides. And it aimed at providing EO Earth observation to new users that are interested on monitoring and modeling landslides. And we were interested at providing to such user a comprehensive interpretation of what was inside the time series and all the interferometric products. And for that, it was why deformation is important for landslides is that it can characterize different, first it can help to detect them in a very large regional scale, and also it can, at local scale, help to understand what processes are going within them. So to do that, so the main goal of the service is to identify temporal and spatial cluster of homogeneous style of ground motion. And using different input data sets, which can be either discrete with point clouds, such as what we obtain with PS and DS in SAR, but also continuous with very large data cube. So the service includes different components with a preprocessing module that will detect outliers, smooth the time series. And then there is 2 modes, which is a supervised and unsupervised classification of the data of the time series. So the first mode is a supervised classification. So we worked with basically 5 different classes, which were predefined. So it's the uncorrelated classes. The linear one, where the trend, as you can see here, the time series is linear, and then there is a quadratic one, and then 3 different linear time series that are characterized by a breakpoint, which will be either continuous jump, and then we'll have the same velocity before or after the jump, or we'll have 2 different velocities before and after the jump. So the second mode is an unsupervised classification, which is quite basic and use the ECA-PCA decomposition and provides the first component of the principal component decomposition or the independent component analysis. So basically, technically one of the main challenge was to be able to process a large amount of data. So we actually designed the service so it could be run on optimized data cubes and use stride optimization to really be able to process the data cube from different from the different dimension of the data cubes, and then like maximize the processing rapidity or speed. So then this service is available within the EO4Apps landslide application. So it's an application that is available on the geohazard exploitation platform, and it's available among different services that you can see here that gather like offset tracking, optical offset tracking, but also interferometric services, and also here's a timestat that is post-processing that can ingest the output of the previous services I mentioned. So services were available for a large amount of users in the Alpine environment, in the European Alp. So they could get access to this Earth observation and get access to some training to understand better how to use remote sensing processing. So how to run the service? So first you have to select the service on the web page. Then you can like select your output from another service or any kind of data cube you want to ingest and drop it on the menu on the right, and then select and tune the parameters that you want to define and run the service. Once you've done that, you also can have access to a tutorial that is available on the same website. And finally, one of the first output you get is a PDF which gathers the different characteristics of your output, such as how many points were classified in the different classes, and also the PCA, how they look in the time series. I will now present like 3 different sites that we tested the service on, which is the Valais Canton in Switzerland, the Mont Blanc Massif in France, and the Briançonnais in France as well. So to start with the last one. So here are the results. So here you can see on the left the velocity, the mean velocity over the region, and you can see that you can observe some unstable slopes that are moving at different speed. And here on the upper left, on the right, you have the supervised output and then the 3 first PC principal component decomposition. And you can see that depending on the principal component of, you are looking at, you will see different sites having a strong weight or not. If you look in more detail, maybe not. Yeah, this is one. So that's a zoom on the 3 precedent area I was showing. So here you have the velocity and the result of the supervised classification, where you see that around the landslide you also have like similar classes than within the landslide, and then the 3 first principal components of the decomposition, and you can see that they have different features especially. If you are more interested on the supervised mode, we provide also like the breaking point, for example, the breaking point occurrence. And here you can see that on the last landslide I was showing, you have like all of them are classified in the same class, which is a bilinear behavior with a jump and 2 different velocities. And you can see that the jump occurred in beginning of 2016 with a quite large velocity magnitude difference before and after the jump. Then on the other side, so it looks like that. So you get the velocity. Here it's a supervised result with the different classes, and then the PCA. And here again, if you try to zoom on one of the landslides, you will get this kind of the same behavior with a gathered class with a breaking point that is occurring in 2018 this time, but with a velocity change that is much lower. The final test was done very recently, so it's very preliminary results. That's the output of offset tracking with Sentinel-2 over the Mont Blanc glaciers in the Alps. And you can see here the mean velocities that you obtain if you process all the Sentinel-2 acquisition from 2016 to 2023. So you can see in the east-west and north-south component, you see different glacier moving.
Okay,
we just processed
okay, welcome to the first afternoon session, to the ionosphere and the atmospheric session. We have started a little bit late because of delays with the lunch. And yeah, welcome everybody. And so my name is Falk Amelung. My co-chair is Giovanni Nico.
Yeah.
And yeah, okay, there are my glasses.
Maybe I can read for you. The first presenter is Felipe Betancourt Pavan, who is going to present a work. The title is Two Words: An Interferometric Autofocus for Ionospheric Phase Signatures in Biomass. You have 20 minutes, and 3 minutes before I will give you the time.
Thank you.
So you get both of them at the same time.
Yeah, you hear me well? Yeah. So welcome to my presentation of today, which is like building the path towards the interferometric autofocus for the ionospheric signatures in biomass. I'm going to, wait, can I? Okay, now. So I'm going to speak about a bit about biomass and about the ionospheric errors. Then I'm going to describe a method for the calibration of the, no, for the, a method for the characterization.
So yes, it's really on the session live. Yes.
Yeah, it's live.
It's live. The live of the other session.
It should be. Should be called.
All right. So some conclusion and perspective. Basically, this service is still like under test and still like in development, but we are very like we would be very happy to have tester and feedback. If you are interested, you can try it for free. And yeah, we are delivering to the point like to currently like many information, and we still have to work on how to provide them in a more intelligible way. And yeah, we are thinking of several updates and developments in the future. Thank you very much for your attention.
Are there any questions?
Maybe I can speak house.
I don't know, the other side maybe don't will hear you.
Thank you very much for your nice presentation. It's difficult. To use the TimeSat tool, you need to process the satellite image in JEP, or you can do it.
No, we actually, like, you can either process it on JEP and use the output of the services on JEP, but you can also use EGMS outputs, and like we'll try to fit those format already.
And if I have my own
yes, you can
results.
upload it on JEP and then use the service. So you will have a data storage, you can upload your results and then use the service.
Okay.
Any question?
No, not yet. It's just very simple at the moment, but that's what we are aiming in the future. All right, thank you.
Questions?
Sorry.
Yes.
Yeah, thanks for the talk and thanks for soldiering through all the technical issues. Yeah, I was just wondering, because you focus on landslides, have you got any hopes to apply that to sort of any other types of hazards or any other deformation signals?
It was developed especially for landslide because it's an application that was not really tested with those kind of like techniques so far. So we wanted to, I mean, other groups did it also this year, so we were in this movement. But as you could see, like we tried it on Glacier, so to see if the service is like applying to different cases or not. So yeah.
Great, thank you.
Thank you.
Thank you very much. Go to the next speaker, David Becker. We'll talk about Opera analysis, Redis-R, and optical products.
Thank you very much. First of all, I'm very excited to be back in Leeds. I see a lot of familiar faces. I did my PhD here, and after I left, I haven't come back since then. So it has been 7 years, and I need to say not much has changed on campus, and somehow that's reassuring and exciting to see all those familiar faces again. But meanwhile, I'm going to go and give you an overview of the Opera project, as well as the different products that we are producing from SAR and optical datasets, and specifically its surface water, surface disturbance, surface displacement, but also a couple of key intermediate products like a radiometric terrain corrected product and a core-registered SLC stack product. So this effort that I'm presenting here, I am the Opera project manager, but I couldn't have done anything here without the whole team. So there's a large team behind it. You will see that in the subsequent slides. But it's also not a single institution. We are working together with many different partners to realize this. So the background and how this really came to existence is the vision of Gerald, who is sitting over there. And he has always wanted to have generated these global products. So there was a mechanism that came to an existence, which is through the Satellite Needs Working Group. These are federal agencies that express needs, remote sensing needs, and then NASA is doing an assessment and recommending certain products. Now that is the opportunity for true Congress to get funding for implementing these products. And Opera is really funded out of the 2018 cycle. So there's these 3 products that I mentioned here before. And on the right-hand side, you can kind of see all of our different institutions that we're working together with, which includes universities like GLAD, which is the University of Maryland, University of Alaska, Fairbanks, as well as Southern Methodist University. Then we have consortiums like EarthScope, which was formerly called UNAFCO, and other partners from NASA like Goddard. Let me see if this is working. No? Oh, there we go. So in terms of the team, really, if we put all the people together, we're a group of 60 plus people, and it can be ranging of people working 20% or full-time on it. And this is just the collection of faces that send their photograph in. There is many more. But just to kind of stress that this is really a large undertaking of a broad team, and it ranges from scientists, it ranges from algorithm developers, computer scientists, system engineers, etc. Not to mention the business office, of course, as well. I will just cycle through the different products and give key characteristics. So the first one is the surface water extent product. We will be mapping this from harmonized Sentinel and Landsat data. So that's Sentinel-2 and Landsat-8. Then we also have Sentinel-1, A and B, as well as NISAR. And unfortunately, SWAT has been removed due to funding constraints, so that one is delayed, as is marked at the bottom, until further notice. But really, by having these different satellites all together, you start looking at surface water extent at a very rapid revisit time every couple of days, 2 days or so. And we're generating this product on a near global scope, and the product has been operationally, or has been in production at least for the optical components since April of last year. So you can go and find these products already on the DAC website, so the Data Active Archive of NASA. For water products, that's a physical oceanography DAC called PODAC. So go and check it out. And then in future, we have different staggered releases, as I will show you in the next slide. You will have the Sentinel-1 that gets added, and then subsequently NISAR. Then we have the surface disturbance product. This one is mapping vegetation changes as well as spectral changes. Again, optical data, but recently it has been has been added to our scope to also produce the SAR-related component from Sentinel-1 for this product. Again, this is a near global product at 30 meters, telling if your pixel has been disturbed with respect to a historical baseline. The optical product has also already been in operations, and this product is freely available again, but distributed through the Land Processes DAC, which is LPDAC. Now we go to more perhaps the products here of interest to this group is the displacement product. So you have the European ground deformation map. I'm happy that this is kind of the vision where we're going to also have a counterpart for North America. So this is a line of sight displacement product from Sentinel as well as from NISAR. Will be generated for every pass that there is data. So the cadence really depends on the 6, 12 days or 24 days depending on the sampling. It's better than 30 meters. It's a full PSDS product. And I will show you a derived example afterwards. But we are also looking at the full historical extent of the mission. So it's not a forward stream product only. So it goes back to, let's say, when the Sentinel-1 data became more stable and around the beginning of 2015. This product distributed by the SAR DAC, which you're all familiar with, is the ASF DAC. Lastly, I want to make note of a notional product. It's not yet funded, but it has been proposed by NASA to OMB and Congress, is the generation of a decomposed product, so a vertical land motion product. And that would be currently only from Sentinel-1. So if that product is realized, you are really starting to have a counterpart with respect to the European ground deformation, but then for the North America geographical scope. Then there are two intermediate products, radiometric terrain corrected product, or the RTC product. This is only for Sentinel-1. NISAR mission has its own product, which is called the GCOF product. This product, we're currently in our validation phase and wrapping that up. It is to go into production about 1 month from today. It's a forward stream product, again, 30 meters. And then we have the core-registered SLC stack product. That's for Sentinel-1 and NISAR. Again, the Sentinel variant is to go operation in 1 month from now. And that, as core registration says, it just resampled to a common grid. And this will be for Sentinel-1 a burst-wise product, and then for NISAR it's going to be a frame-based product. So here is the timeline that I was talking about staggered releases. We're really trying to get the algorithms matured, implemented, and get them out to the users as soon as possible. So the top row is what we have already realized. We are in operational production for those. And then you can see the second row, Sentinel-1, RTC, and CSLC products. They're coming up, starting production next month. And then what you can also see the next row under the kind of the products that are coming down in the years to come. You can't see here yet the SAR disturbance product. We still need to add that up to it. You can also see the NISAR launch date that is currently planned, and you can see that the NISAR related products hence come a little bit after the NISAR launch, so we can use the validated and calibrated products of NISAR. So I'm kind of giving you some of these snapshots of these different products. So here is the Dynamic Surface Water Extend product. For the optical one, you see that these are multiple satellites combined. This is the Landsat 8, then the Sentinel-2A and the Sentinel-2B. And what we're doing is we're classifying whether a pixel has open water, so fully water, partial water, mixed classes, or has no water at all. That is labeled over here in that, and this animation is just a 1 month snapshot of the products. Again, available, so if you follow that QR code, that's where you can go ahead and download the products. Now, the key thing is that we can go ahead and start complementing this with the SAR data once it becomes available. So the algorithm team led by Haresh, who's also sitting in the back, has been developing this, and we are maturing that for Sentinel-1. So here you can see the example of the optical, where you have cloud cover as a main limitation, and then complemented by the SAR, where you can, of course, penetrate through it, and you also have a little bit of sensitivity to inundated vegetation, etc. So really what we expect here for Sentinel-1 versus what we will have with NISAR is that for NISAR we will definitely be mapping all the wetlands. For Sentinel-1 we are committed to do it in the herbaceous wetlands. Going down to the surface disturbance that we have, again here, this is for the optical data. So we had recently a lot of fires in Canada, impacting much of the North American continent, and here you can see the burn scarp extent. Again, like I said before, this is a time series derived product with respect to a temporal baseline, so we're trying to get rid of the interannual variations, and that product is also pretty well suited, given that it does vegetation and spectral changes for urbanization, landslide mapping, etc. The key thing is we're not adding any sort of attribution to the change. That's what we would expect that the user would do himself, being the expert for that area. Again, this will be complemented with a SAR-derived product in the future from Sentinel-1. Then the surface displacement product, if it wants to pop up. Oh, there we go. But I think I might have skipped a couple of slides. So no, I was mistaken. So the next one over was the RTC product. So here is a snapshot of as we have produced the data in our current processing system for the globe. The RTC is going to be again available in the next month from now, and you can see on the right-hand side an example of what it does. It really removes the impact of the topography, highlighting some of the changes that otherwise or some of the features that you otherwise would not be able to see, like urbanization, thinking about forested slope, glaciers, etc. So we are going to be using this as an intermediate product for our water product, as well as the displacement product, the disturbance product. Okay, then we have the CSLC stack product. As I said, we have the North America geographical scope, which is kind of shown over here. This product is co-registered, corrections already applied, so you can just do cross multiplication to go to interferometry, or you can start thinking about on-demand coherence change, etc. Again, next month this product will be available, and I would encourage people to go to Haresh's talk in the other room after mine, where he will give more of an overview of the ETAT corrections as well as the algorithm background. Then here, the displacement product, this is going to be frame-based, again, line of sight. This is further out a year from now, can be used for tectonics, subsidence, generally whatever everybody's doing in the room, it should be suitable for that from an INSAR perspective. I wanted to talk a little bit about the notionable product. Here I kind of showed an example on how it could look like when we derive it. Really, we take away the relative nature of the INSAR, the ascending and descending, and move it towards a mosaic product. There is going to be a poster tomorrow from Marin, where he's going to give more details about this product in specific and how it could be looking like for Opera. Then okay, so then I wanted to again talk about the data access. Everything is free and open at the different DACs. So this is the links for the water product as well as the land disturbance product. If we go towards the SAR DAC, which is LP DAC, they have their own product page, which is the Vertex page, which is shown over here. Again, they provide value-added services that many of you are familiar with already, and that will be similar for the RTC and the CSLC product. There is also the Earth data page, which generally where NASA have all of their data sets. You can search just for Opera and find the products there that are currently available, and the future products will be there as well. So, and then I'm going to show one more slide here on data access and discovery, which is the visualization. So I showed you that imagery where the products come in, and you can see the footprints go over time. RTC products will be there as well, which are mosaic, so you can start looking at animations and global analysis relatively straightforward through that service, and it's called Worldview. And lastly, I wanted to kind of talk about the different resources We are also committed to be full, open, transparent, and reproducible. So all our code is in the open domain for people to play with, reproduce the products, and even the system is there. So I invite you to go and have a look. And lastly, we are always looking for input from others. So we have working groups. There are already a lot of our European partners participating in. But if you're interested in providing feedback, either on the products or using some of the early products, please join us on our mailing list or shoot us an email for any ways on how you can engage. Thank you.
Thank you, David. Very impressive presentation. Is there any questions for David? Perfect on time.
Okay. Good.
Yeah, maybe Anna.
I was just wondering if you have compared your products with some of the other available data sets. So, for example, the surface deformation, is it effectively similar to the Comet Lixar type thing, or are there differences?
Yeah, so we're currently prototyping based on a lot of the area products. I mean, they're pretty similar to the Lix products. For Opera itself, we are changing the way on how we're processing. It's not pair by pair processing. It's a full time series approach from persistent scatterer and distributed scatterer. So we are expecting differences, and I mean, our expectation is it would be better from the conventional pair by pair processing.
Just a very quick question before we move to the next speaker. So you are generating this geocode SLC. Are you using it for generating the displacement product?
Yeah, it's our intermediate product for going to displacement, and we thought it would be a very valuable product because you don't need to do the co-registration anymore. You kind of cut away a lot of the processing. Hence, NASA was willing to make that available to the community and archive that.
Right. Thank you very much.
Thank you. And if people want to have some stick posters or like bookmarks, I put it here. It gives a summary of each of the different products, so it might be easy on the plane.
So we move to the next speaker. The presentation will not be given by Francesca Casu, it will be given by Fernando. And we talk about how space-borne and airborne INSAR products can support the civilian protection.
Okay, good afternoon, everyone. My name is Fernando Monterroso. I come from Irea CNR in Naples, Italy, and Dusseldorf. And now I will basically present the different automatic tools that we are developing for monitoring the seismic ranges and also volcanic areas in Italy and other parts of the world. So this is my presentation. I need to wait here. Okay. Already out knows we developed in the operational service to EPOSARF. There is an automatic generation of seismic displacement maps that we generate more or less 5 years ago. This is the big catalog of the different DINSOR products for different big earthquakes or significant earthquakes around the world. So basically, this automatic tool is put in function and auto-supervised in an automated way DINSOR products for scientific community, specifically for the Civil Protection Department. In this case, we developed these automatic tools to put all our data in EPOSAR service, TC, and also the hazard exploitation platform. This is the BAESA. So already we are processing more or less the 605 earthquakes around the world with more or less 45,000 products with interference and loss displacement maps and also coherence maps. We can check here the EQ for check with our information, and this is obviously respect to the standard variable of data of the EPOSAR data. So we can check here. This is the web page of the portal. We need UK access to the visit and check on our data. With this case, recently I brought this occasion for show you the different ecosysmic interference from Morocco earthquake with the past Saturday. We can see here the ecosysmic interference of the above the both interferometric pairs, the 12 days and also 24 days for Sentinel-1. And also the lost displacement maps. All these products already available in a post job portal. So the next generation about this automatic tool is the pre-operational automatic source modeling by using the EPOSAR products. We are developing with colleagues and Simone Azzori from National Institute of Geological and Volcanology in Italy. We are put all our catalogs to develop in an automatic way the source modeling. In this case, we are developing the fault solutions for different earthquakes. More or less, we take about the 100 earthquakes. These results are put in and also in the future in our catalog. We are working now in the metadata. If you are interested about this research, we talk about the next Thursday for more details specifically for this automatic tool that we work and developing now. You can check and also the QD paper that we are publishing recently. So this is in concern with earthquakes. Specifically we have the monitoring earthquakes around the world with different earthquake magnitudes with 4.0 to 4.5 for European area, specifically for Italian territory. And for the rest of the world, we are show you that we are processing more or less earthquakes with different magnitudes and different significant earthquakes around the world. So we talk about to do volcanic areas. In this case, we create an also non-supervised way the operational service to run the information monitoring of the Italian volcanic cases, volcanic areas specifically to support the Department of Civil Protection in Italy with the seismic crisis of volcanic eruption crisis. In this case, we developing the automatic mode, the generation of the products. Using the Sentinel-1 images, we create this automatic tool and also to generate in wave mode the loss displacement velocity maps and also the combination. So basically, we are using all the satellite images as Bible Finds 2015 for the above orbits. In this case, this example is for the Napoli Bay area. We can see here the track, ascending and descending track. We are using then also the algorithm developed in IREA CNR. In this case, we are using the PS-BAS algorithm. This is Manunta 2018. That basically is this algorithm is adapted to processing the Sentinel-1 images to interferometric way. So we generate the loss velocity maps for the both orbits, and after we combine this information to generate the time series. This is the information that we basically use to create to report, let me say, to support the civil protection for every month that we need, we perform the meeting to report about the different seismic areas in Italy. Every time there is a new acquisition for Sentinel-1, for example, if we participate in 1 month in one meeting, so we process more or less 3 satellite images and the coordinate and more. So in this case, we add the satellite images to add to the loss deformation velocity maps, ascending and descending for to create the combination, we say, the vertical and horizontal displacement maps. So basically, now I will show you some results. We can see here the Campo Ferrei caldera, the most beautiful place around the world. In this case, this caldera, obviously, you can know that the Campo Ferrei is an upfleet more or less the 1 meter in the last 15 years. So this is an example for the Campo Ferrei caldera. We are processing more or less 400 images, the Sentinel-1, B and A, so now just 1A. And we are processing more or less in the total of 11 and 86 interferometric pairs. So this is an example for Campo Ferrei caldera. We can see here and also the trash of the line that basically across all the city. We can see the up in the center of the Pozzuoli Square in the Naples. That represent more or less the deformation of the 1 meter in the last 15 years. So the next case is the Etna volcano. It's another significant important volcano in the south of Italy, specifically in Sicily. In this case, we can see here more or less the deformation pattern in the area of the volcano. But since 2008 and the end of 2008, we can see experimented this jump under the earthquake with Fandiaka fault for 4.8 magnitude. So we can see here this jump that occurs in this volcano. So every month, obviously, we support the civil protection to report, which is the behavior of this volcano in the south of Italy. The other case is the volcano Iceland. We can see here the other interested cases. In these cases, we are processing the same amount of images for the both orbits to generate the loss deformation velocity maps, and also to combination the vertical and horizontal displacement maps for in this case of the volcano Iceland, of the Eoli Iceland in the south of Italy. For this case, we are see you here at this unrest that occurred in the last 2 years ago in the area of on the crater of the volcano. We can see here more or less the unrest that occurs in the September, November in 2021 and different area of the volcano. So basically, for this volcano, we are submitting the paper for understand what happened when it unrest in the area of the crater volcano. So we can check in the future, maybe we don't check this paper because now in this phase submit. The other cases is the area of Stromboli volcano. We can see here the Iceland. It is, of course, this big volcano in the area of the Stromboli. We can see here the same deformation pattern in the time series for the ascending and descending orbit. In this case, we can see here this small deformation pattern in the area, change deformation pattern in the area of the in the year of 2019. And after the other small change of the pattern in the end in the autumn in 2022. So specifically for this case, we are we are working in the group, in IREA CNR group, with the pre-operational service to airborne SAR system, specifically to create the airborne X-band interference SAR. We are working with the static antenna in this area for the study of the Sciara del Fuoco in this area. This is a volcano, on the Stromboli volcano. So we are created on the single pass interference to generate a digital elevation model. In this case, we can see here which is the different the 8 October in 2022. So, which is the conclusion of the future perspectives about these kind of activities. We can monitoring and support the civil protection department in Italy to create different results to earthquakes. In this case, we are now development. We need to be operational system. We need to be operational group to create the operational EPOSAR service. In this case, standardized products available through EPOSAR infrastructure. Support, obviously, during the civil protection department in Italy or in other areas of the world that are interested to check this information. During the seismic crisis, for example, now in the Morocco earthquake, we create now the interference, and now, in this moment, it's supposed to maybe is available now the automatic modeling of the slip motion of the area of earthquake. So basically, we are pre-operational automatic seismic source modeling. That the next Thursday I will speak along this topic. And about the volcano monitoring, we are satellite. We have satellite operational system that maybe we can create. We can update the different loss deformation velocity maps and loss time series in the area of interest of different volcanoes in Italy, in the south of Italy specifically. And an airborne system, and also we are working with pre-operational airborne sound system to monitoring and with more details in this area. Continues to support to the civil protection department during the crisis. So the next challenge is analysis and interpretation of measurements. Specifically, we are developing and also artificial intelligence to understand which is the technical interpreted analysis to this data, and moves to airborne system operational practice and the next constellations that we are waiting for to present the next results. So this is all. Thank you very much. This is my Twitter. I'm active in Twitter when I put all my information. you have questions.
Any question? No? I will fire one. So I understand that you have a really operational services with a clear clients identified there, or clear customers identified behind your service, which is sorry. I understand that you have a very operational service here. Yes. With customers well identified, being the civil protection. So could you tell me what was the impact of the loss of Sentinel-1B into your services?
Oh, the impact is really interesting. So, even to the seismic crisis, do you know, to Italy has more or less 5 volcanoes in constantly activity. So every time the past week we have experimented in Naples, specifically the earthquake, more or less the magnitude 3.9. We need to create in automatic way these results to be operational and to respond with emergencies, specifically in these kinds of events. Obviously, we talk about the Etna volcano. Every month we create more or less, we adjust in our system more or less 3 images. So we need to be attentive to do available the images to create two different maps, and also because we need to attend to different meetings to show that our results, and these results we can take different decisions about to do behavior of volcanoes. Yep.
What's the resolution of your seismic data you're using?
What is the resolution?
Resolution of your seismic data you're getting?
Oh, okay. The resolution of the results of in this case is 20 meters.
20 meters.
Yes.
So anything below 20 meters you cannot detect, right?
Yeah. Okay. There's another question.
Another question? Don't be shy.
Don't forget that the next Thursday we can talk about to do automatic modeling. That is the next generation of the next step of the automatic tool of earthquakes, the Sentinel-1 products. Okay. So thank you very much. Okay.
Thank you very much. Cool.
We move to our next speaker, Michael Fumelis. They will talk about the nationwide Sentinel-1 PSI surface motion of Greece using on-demand snapping service and JEP.
Hi, good afternoon. My name is Michael Fumelis. I'm coming from the Aristotle University of Thessaloniki. I'm showing you like another operational service. There are a lot, which means that we are quite mature to reach the level of having services and not like discussing still the processing. I will show you an implementation that was done on the geohazard exploitation platform. It's called snapping. And I will show you an effort to do a user-based production at a national level. So the difference with the previous presentation is that a user is processing himself. He can produce the product himself on a platform compared to the other services where you find like a data-ready, analysis-ready products. So I'm coming from the University of Thessaloniki, as I said. We are a small group working on Earth observation and geohazards. We are trying to collect everyone who's working in the university in a common umbrella to have, we have built what we call Center of Earth Observation and Ocean. And this is to gain the advantages of multidisciplinarity between the team. Next slide, I don't think, why it's moving too fast. I can do it backwards. So I don't think I need to show you this slide. Everyone knows here SAR, and there are several people that did that even before me. So we will focus on the persistent scatter analysis for this talk. This is an initial version of the tool that we developed together with Jose Manuel using the ESA Snap toolbox and the stamps developed by Andy. This slide shows you what was the situation back in 2012 before the Sentinels were launched. Everyone was awaiting that we will be bombarded with a large data set and we want to go to this operational stage processing and we need to deal with all of this big data analysis. And at the point, a lot of people already from here were at this time in Santorini in Greece, and they proposed that it's good to have like a system okay. A system will take advantage and process automatically all this data set, and I think that was the initial part that ESA thought of the exploitation platforms, and JEP is one of them. JEP is focusing more on the geohazards. So there was a need from the community, in fact, and this was built. One of the solutions was JEP. Okay, this is the JEP interface. In fact, if you go today here, there is a post about the recent earthquake in Morocco, so you can find the interferogram as well. And this is what we did. We took the ESA Snap toolbox, which is a powerful tool. It's not only for education. And the PSI processing that was developed, stamps that was developed by Andy. And we tried to optimize that in a processing chain to implement it on the platform. So we have also the idea of not to avoid reprocessing everything from scratch once the new acquisition is made. So we split our processing into two. Snapping IFG, which is just to generate all the interferograms and store them in the platform. And then on top of that, you just run the PSI later on, and you have the time series solution. So each time that you have a new acquisition, you can generate the interferogram, store it there, and depending when you want to have the PSI solution, every one acquisition, every month, every 3 months, you can update the solution. This is saving a lot of resources and time for the processing. And this storage is stored locally on the platform for future use. So this is the idea. The services as we built them was the snapping PSI medium resolution and full resolution. The only difference is that we are merging the point scatterers at the medium resolution to have lighter product. So the idea was just to have the medium resolution one, which is able to run over very wide areas. And then if there is a signal, interesting signal, you can focus later on with the full resolution one. The PSI, the PSDS, PSI Plus we call it, it's not integrated on JEP. It's something that we will do in the future. This is, right now, we are processing locally at the university. Then this is the interface of the services. So this is the IFG, PSI full and PSI medium. You have user-defined parameters. Here we need to decide where to go because real experts want a lot of processing parameters to control and produce, but non-AO experts just want like really the basic. They want just to click on a few buttons and get the results. So we find out like the medium solution to provide at least to ensure that even if a non-expert run this one, will end up with a robust results and not an erroneous one. So this is the IFG one, you run it. These services are being integrated. The operational one is running a year now. This version, another version was like 4 years ago. And it's being developed and upgraded all the time. So this is an example of what we get. This is the airport of Thessaloniki. This is the medium resolution one. It's 100 meters per pixel. And this is the full resolution. And this is the time series that you can get from that. Now, in terms of outputs, you have the PSI outputs, you have the normal one, code, latitude, longitude, all the time series, some specific columns of interest. And there are several products that you can get from the processing. One is the CSV with the time series, shape files, some browse products. And finally, we have added recently this HTML code, which was requested by users. And this is a simple file, a file that you can open with any internet browser, and you can browse the measurements. And this is nice because you don't need like a super sophisticated geospatial tool to see. It's a way to check the results quite quickly. This is initial work that we did over the Nile Delta. And we generated, that was the first time, in fact, that we tried a wide area processing. And the idea is that we had a platform that has some capabilities. And until now, we were processing small areas around the world, local parts. So the idea was to just try to use the system to see its capabilities. So that's why we went to the Greek, to process the entire Greece. To do that, we figure out that it would be better not to process the entire frames, but to split them into tiles. This is to avoid also some propagation of error at the corners. So we split the area into 54 tiles, 90 by 90 kilometers approximately, and we ensure to have like 10 kilometers coverage from all the sides. This is just to have all this information in case that we want in the future to merge all the data set to put it in the common frame. We process from 15 until 2021, all the entire archive. And this is the result. That was announced. The processing was, in fact, completed last year in September. We announced it somewhere in Christmas that we will put all this result on JEP. The story is that the platform was not ready to have a new visualization tool. So we decided to wait until this visualization tool comes. This is the frames that you see that we process, like it's 6 tracks, around 4,000 SLCs, 4 million points at medium resolution. And an example over a small area. In fact, this is the area where currently we have the major floods in Greece. And we receive a lot of questions whether this flooding will cause like acceleration of motion there or something. A lot of people are asking. So this is the visualization product that I received yesterday from JEP. So we integrated everything on the platform. All this visualization is based on the very nice concept that the Norwegian did in the Norwegian ground motion service. It was an excellent browser of the data to check the time series. Don't worry about the colors because they didn't tune nicely the colors. It was fixed by 4 plus and minus 4 millimeters per year. So this is a very nice map, in fact, to cause panic in Greece and start. So I will I will avoid interpreting that. So remember this one. It's much better. It's greener. So this is operational. This will be open. It is open to public right now. So if you go to the JEP and you have only registered, you don't need to pay anything. You don't need anything. You can go to this area here under GMS, because also on JEP they have integrated all the GMS, EGMS products, and you can use this. These products are really nice because also you can do validation between the different measurements and so on. And again, I'm saying that these ones you can even produce yourself. The advantage here is that if you have this data set there, and if you want a specific tile, you want to update this specific tile, you can go and update the interference of this specific tile and rerun the PSI and have the solution. You can have the medium res, the full res, so you can do whatever you want using this data. And of course, you can download the data and use it as they are. So here comes the question of the verification and validation of the products. In that step, we didn't go to the validation with other geodetic techniques. So we said verification, and we verified our measurements with an independent tool, which is also integrated on the geohazard exploitation platform. It's the PSBus from the group of CNREA in Italy, in Naples. So what we did is we run snapping, we run PS bus. This is the difference for the common points, and you see that there is a consistency between the products. We did that not only in Haiti, but I did it in Thessaloniki because this is the area that I'm living now. So you see that there is a consistency. Of course, there are slight deviation about the techniques, but in general, they are consistent. And consistency also is shown not only in the velocity, but also in the time series. So more or less, we are getting the same time series. I'm not picking the best ones just to show that like it's really consistent. But it is, this is important, very important, because till now, when we talk with non-expert, they're a bit reluctant on using or exploiting the data. They think about the accuracy and so on. At least I think once you have two services where users can run them themselves and they can see that they can get the same results, and even compare with EGMS, I will show some slides later on, this gives more credibility to the entire techniques and so on. So this is also the case over Surabaya in Indonesia. This is snapping and S-bus. So the techniques are different. The processing is completely different. So you can see also here, you can grab this bridge, which is not here. But so this is the points which are not common, are not within 100-meter pixels a distance between them. So you see that PS bus, as expected, you can extract more information, more spatial information about the product. This is normal, but still PSI is performing quite well, and it's also grabbing some man-made structures. So this bridge here. Now we are working on updating also the height in the interferometric processing, just to ensure that these points will fall exactly on top of the bridge. So also this is another validation for a moderate earthquake. I know that PSI is not optimum for processing of earthquakes, but this is really slight motion. What we did, we run S-bus, PS bus on JEP in IFG mode, so interferogram. So this is on the left side, the interferogram, and we extracted this exactly from the jump that we see from the time series of SNAP, and you see that the results are more or less consistent. Another thing that we work all for this verification thing is, as expected, to use also EGMS to see how if you are doing well or not. So EGMS now, you have the specific products for the specific geometry that we used also here to generate the grease results. So this is the EGMS, the one from snapping. If you go also to the full resolution, you see that it's more closer to this one because this is run at full resolution. And if you check the time series over a point here, which is the most deforming one, you will see that it's not that the velocity field is consistent, but also that the time series show very high level of consistency. Once we saw that, we realized something else, that we have other seasonal signal that you can see here, or a bit more noisy compared to the EGMS. So we thought that there is also a filtering procedure applied to the EGMS. And surprisingly, when we were checking these results and the consistency between this data set in an area, in most of the cases in Greece, it was fine. But once you are checking that in areas where you have an earthquake, this is there is a deviation in the results. So what you see, for instance, over this point here from the two data sets, is that here they are really smooth, and the effect of the earthquake is not considered. So the jump caused by the earthquake is kindly, not only temporarily, but not only spatially, but also temporarily smooth. So this can cause some problems sometimes in the interpretation of the results. I'm sure that I'm not saying that EGMS is bad. I mean, this is an excellent, really excellent product, but maybe in the cases of earthquake, it requires a bit more hands-on to remove this effect, which is more something can be done here. In the filtering procedure that you can apply also in snapping, you can avoid that. So here also snapping medium resolution for the earthquake in Tirnavos. It was 2021, and so you can see here over the area that is more affected. These are the consistent results between the two data sets. You see that more or less, I didn't apply any calibration between references and so on, but the results, the patterns are exactly the same. And the time series, as I told you just before, they're a bit different. So here you see the jump of the earthquake and some seasonal pattern because it's an area which is also a lot of groundwater variability there, which these ones you don't see that in this specific time series. But this is only in the case of the earthquakes. Apart from that, there is a consistency between the data. What we are doing with these data sets, and we are doing other geometries, so on, is to focus on the formation for each of the cities, extract some nice graphs, and see the amount of population affected for each city by potential ground motion. So this is some different examples from areas in Greece, in big cities in Greece. In fact, these are the cities that we had also the land cover from the ESA land cover atlas. Okay, so here I need also to how this was done. That was done by the support of ESA. Of course, you are running something on the platform, but you need the resources to run all this stuff behind. So we did that with the support of the ESA Network of Resources initiative. In fact, everyone that wants to use these services, not only this one, but other ones that are on JEP, they can use this initiative to get the funding for the processing, and they can get the results from. This is I'm done. Thank you very much for hearing.
Thank you, Michael. Any question? You have some minutes still for a question.
We are 10 minutes ahead schedule, so you have to say 10 minutes on the grill.
I can go
you
through all the
can dance,
presentation.
you can do some Greek dance, or what can you do? Now, is there any question for Michaelis?
Yeah, just one question. I'm wondering if, for example, big infrastructure people like harbors or whatever are using your data, and what for? And can they use their data, or are they keen to use your data?
The question is if they can or they are keen to use it, because it's different.
Let me say if they are keen to use it. Yes.
I think with the EGMS, that was like a real push to the community to see that what we can do and what we can extract from the data. There's complementarity because with EGMS you have like fixed processing. It has the advantages and disadvantages. If you show them also that you can go on a specific site, do something else more detailed and local stuff, and you are consistent, I think they'll start using it, yes.
Thank you.
Yeah. But not showing the map with the red dots. It will not.
Another question?
Yes. Sean.
Thanks, Michael. I'm just wondering how you managed to capture multiple wavelengths of a jump in a time series on your earthquake examples.
The jump, you mean? We were cutting the processing. So we were running the processing as it is, but in the step of the filtering procedure, we were not filtering like the entire time series, but we knew exactly the time of the earthquake. This is not easy to be done in an operational service for entire Europe. So here I was controlling the processing myself.
And then how did you
You see the jump, but as we know from the PSI, I'm not sure that this jump is the entire motion of the earthquake. At least you avoid showing like something which is smoothed like before and after, because what's happening that most people start asking, was there a signal before the earthquake that we didn't notice? It was going down before. So you just avoid this kind of question. I'm not saying that doing that for an earthquake would be the best chance. Even if EGMS will find a way to custom this case for the earthquakes, the jump of the earthquake might be underestimated by PSI. But no special processing was done for that.
So there's something that I like pretty much in your presentation, which is the fact that you have been able to show the difference between two different processings or two different processings, and trying to use that as a way to validate or verify your processing. And I think that we have seen that, and maybe that's more a question for the seed questions. We have now a number of platform or services that are providing similar type of information with different type of processing. But in the end, it's always the same thing. If the way to access this information is totally different. So if a user wants to access the data from the platform A or from platform B, it has to really to apply a different way of accessing the data. So since we are talking about the same type of signal, would you recommend that those people try to work together in try to have a harmonized way to access this information, such that it becomes a bit more transparent and easy to get processing or to get time series from different platforms, different processings, and merge them together in order to verify or to get more confidence on the processing?
I'm not sure that we need really to merge all the data from different providers, because it's good to have several people running different algorithms and doing different things, because I'm sure a group doing much more than what we do, others do differently. The only thing that we need to ensure, and this is coming even from what I saw before, I was running something which is more or less automatic. I'm using the GenArea chain was also automatic. I was not trying to do anything. I was comparing with data sets which were published from other groups with other algorithms, and they were showing consistency. So I would say, depending on the algorithm and the location, you can use one performs better than the other, but at least a message would be that we are now at a good stage to maturity to say that more or less we should get the same results. So, but you can never stop other people, like ASF is doing like also very nice time series and so on. So.
Thank you. I think that we can move to the next speaker. Thank you very much, Michaelis.
Now, next speaker, Giulia Tessari, will show us a land motion monitoring service of Switzerland.
So good afternoon, everyone. I'm Giulia Tessari. I'm working at Sarmap, a Swiss company, and I'm presenting here the implementation of the deformation service over Switzerland. So just to give a context, you saw already many times this European ground motion service. Unfortunately, Switzerland is not part of Copernicus, so the Swiss Confederation tried to cover, let's say, this gap and to implement a similar service over Switzerland. And so the company I'm working with was in charge to do it. The results I'm going to show, and what I'm going to show, is mostly the implementation of the service, as the results are not published yet. So I'm not focusing on analyzing what we could detect, but more what were the main challenges, as Switzerland is actually a pretty complex environment. What's going on? Okay, so the area we were working with over was Switzerland plus Liechtenstein, and a buffer 5 kilometers all around Switzerland, so a territory of roughly 50,000 square kilometers. And I don't want to do a touristic advertisement, but everything that is a beauty for Switzerland is actually a challenge for who is processing SAR data. So really high peaks, glaciers, glacier lakes with mountains, everything is green. You know, Switzerland is known for the greenery all around and nice forest. So you for sure know what I'm talking about. I don't need to explain why this is a challenge, but actually like 60% of Switzerland is covered by Alps. Is like 13% of the Alps are actually located in Switzerland. We have 30% of forest that I don't have numbers about the snow cover that is recently changing pretty fast. But we have peaks of more than 4,000 kilometers. So 4,000 meters, sorry. So just to say that I think it was making sense in this case not to run everything automatically, but to spend a lot of time trying to tune the parameters to see what was the best way to extract the best possible information over this area. So we were working over 5 different tracks, 2 ascending and 3 descending. The first part of what I present here is from the starting of Sentinel-1 mission up to November 2022. So it was about 400 scene per track. Obviously, we are going on with the updates, with yearly updates. So here you see the mosaic of the ascending and descending. And here is the coverage of the tracks. This is another challenge we were facing. So when Sentinel-1 mission started the first year, the acquisition were not really regular. So you see like these timelines where I show some gaps on the acquisition. From the technical point of view, the best choice would have been just to cut everything before November 2015 and start with a sort of continuous acquisition, series of acquisition. But obviously, when you have a tender and requirements, you need to respect the requirements. So we needed to ingest all the available scene. That could somehow create problem, you know, when you process multi-temporal analysis, having long temporal gaps is for sure an issue. You can also notice here we were somehow preserving some overlap between the tracks. That was part of the quality control I will discuss later. So I'm not spending much time on the algorithms because you perfectly know what are PS and this bus. So we were asked to provide both persistent scatters and distributed scatters, as is the status of the art for any service. Our approach that we call enhance S-bus was basically processing the S-bus and preserving the low pass components, so the displacement, time series, and elevation, somehow to initialize the PS and to retrieve and to preserve the high frequency temporal components of the time series and extract the PS later. Here is basically the same. I'm just highlighting that from this processing chain, we extracted different kind of products that are somehow in line with what the European Ground Motion Service was also requesting. I will give more detail about the products. But just to know that there was obviously a part of the process is automatic. So the ingestion of Sentinel data every time we have new scenes. So what could be automatized is automatic. But obviously tuning the parameter and some decision on the processing implementation were actually requiring a lot of human discussion and intervention. If you want more details about the algorithm, we have a poster tomorrow that is also comparing this, what I call enhanced S-bus with a enhanced PS. So we also have another multi-temporal approach that is still providing PS and DS. This is the description of the products. We were required to provide all our results in tiles with a grid of 10 kilometers, 10 kilometers, sorry, as requested by Swiss Topo. That is actually the institute that is supervising this project and our contact point. So we provided both shapefile and GDB geodatabase, both slant range results so SAR geometry, line of sight deformation, geocoded products, and also the combination of ascending and descending in a raster grid. This is one of the big challenges if you work in mountainous areas, so atmosphere. To try to reduce the atmospheric artifacts, as if you try to process data as they are, all the Alps are moving, so everything is moving. So we try to reduce as much as possible the atmospheric components, exploiting the GACOS platform. So we were using the tropospheric GACOS correction provided by the Newcastle University. This is obviously not enough because of the resolution of this data. So we were also running as an additional phase eye correction screen, trying to be careful because obviously the size of the window is really tricky. Like the risk is to remove some real movement. So we are working with a pretty large phase eye correlation windows. And then finally, we were also exploiting the multitemporal component of the high pass and low pass filter of S-bus and PS. Obviously, we could correct a lot of artifacts due to atmosphere. Still, it was not completely removed, and I mean, expert eyes can still see it. The other big challenge was the snow cover, because I mean, most of the area is Alps, but still we have some like plains, some cities, so it's not that all Switzerland is always covered by snow. There are some seasonal period with snow, and depending on the elevation, snow is affecting the country in different ways. So here is an example what the EGMS is doing. So there is no a common approach, obviously, because every country has different issues. In the Alps, you can see that they were somehow preserving a continuous time series. You will probably notice it's a bit more noisy with a sort of seasonality, so probably when it's snowing. While for example, Norway, they decided to mask out all the snow period because it was more homogeneous, let's say the temporal snow interval. I mean, there is no right or wrong, it's just a choice. So in our case, because we were in a situation in between the two, we decided to apply a selective mask that was working only over some period of the year and only over some elevation. So our results will show some continuous time series where in the plain or over Zurich, Bern, over the urban areas, and the Alps or part of the Alps over a certain elevation are somehow masked to avoid some misleading information that could be extracted during the dry snow period. And obviously, I mean, the melting and snowfall are already somehow automatically losing information because of the correlation, but we have some coherent period with snow that somehow are providing misleading results. So we were just masking over some elevation to avoid to compare like the ground and the dry snow periods. Then there were a lot of quality controls as it was requested by the tender, obviously. So we got GNSS point. We had to verify the quality of the atmospheric correction through some short interferogram variograms to see how the correction was working. We needed to guarantee point density based on the land cover plus consistency on the overlapping areas. So the controls where we try again to automatize as much as possible, but obviously some calibration was needed. I just show you some of the quality controls we ran. So I show you before the overlapping among tracks, but also among bursts. So we were somehow verifying on the overlapping area, the consistency of the mean velocity, and we got to a mean difference of less than 1 millimeter per year and the standard deviation less than 2 millimeter per year, while the comparison with GPS that were stable points was really small in terms of mean velocity, so less than 0.2 millimeter per year with a standard deviation almost 3 millimeter per year. And this is another layer that we were asked to generate, so the density map. And again, this is somehow always tricky to guarantee the quality of what you provide, but the density as well, because we know there are some areas where there are the correlation. There are areas with fast movement that go beyond the capability of the technique to measure this displacement. But obviously, we need to find the best compromise between the point density and the quality of the points we were providing. I just go back, because, maybe no here. Okay. So we reached the point where we generated all the historical displacement. We also work in the first year update and working now in the second year update. The resolution of the product is, let's say, the best resolution in case of PS, 5 meters times 15 meters, while for DS we got a 30 meters times 30 meters resolution. Some interesting things that we were asked to provide was the percentage or the number of the real, the image that were really used, the interferogram that were really used in every time series. And in case a point was somehow a part of the time series was interpolated, this information was provided. Because who is using the data, finally? Want to know if it's something the SAR is doing, something that is coming from our interpolation. So we had additional field date by date stating if this was a measure point or interpolated point. And yeah, so to conclude, this is what we reach up to now. So creating this historical analysis from 2015 up to 2021, then the first year update. And there is another year update that is due. Obviously, we verify the capability of measuring slow deformation trends. Still, there are a lot of really fast landslides where there are ground truth, and we verify we were not able to describe this fast motion as well as glacier, and it was not a request actually, so permanent snow was fully masked. So the idea of providing anyway a service at national scale is not completely substituting the local scale and like specific case study of landslide or so. There are still something that both in terms of temporal updates that in terms of tuning of parameters cannot really be fully described by a national scale service, at least in our experience over Switzerland. So thank you for your attention.
Do you have any question?
Well, there, and then Erish.
Yeah, sorry if you said it already, but maybe I missed it. Who is using your data at the end? Like,
Sorry?
Who is using your data? I mean, for who do you provide data?
Swiss Topo, so the Swiss Confederation was paying this service, and Swiss Topo, that is the National Institute of Geology.
I got that, yeah, but for who at the end? I mean, do you think for
if they
who
decide
wants
to publish the results, they will be open to, for sure, the research institute and possibly to the public. But
Okay,
it's
but
not
as you
our
said,
decision.
for research, maybe like local studies are better. Because are you precise enough to give good data, like for landslide, for example, or you think you have the accuracy to give good data for landslide, or?
Yeah, I mean, this is one of the parameters that is included in the metadata.
Thanks.
Thank you.
Thanks for the presentation. I was wondering for the masking, at the end, how are you doing it? Basically, are you using ancillary data?
No, I mean, it was one of the options, even trust coherence, but it is becoming a second process, like creating mask day by day. So we were somehow verifying the last decades, the behavior of snow when it was snowing, and we did some for a few years, we did some analysis both on optical and coherence data. And we decided to mask everything from 1,500 meters up from November to April, and thinking that before and after the coherence should do its work. Like, because if there was snow melting or if it's snowing, everything else is going to be masked by the coherence. Obviously, it's not super fine. It could be better, but still, when you work at national scale, it's already a compromise. Better than masking everything or preserving noise or errors.
Thanks. And just a comment on your verification across different subswats.
Yeah.
Well, I think, do you expect that always be consistent? Because I wouldn't, basically. I just have a comment.
Yeah, let's say that we were using some calibration points in the overlapping areas. So the reference point we use for calibration, then the final product was calibrated on GPS or part of GPS we got. But there were some previous internal calibration.
Okay, so just to be clear, basically, the incidence angle is different from this subswat.
Sure.
So the same signal could be different.
Yeah, sure, but it's still like Sentinel is not having a huge angle from SWAT to SWAT. It's just a small variation. And it's still, I mean, we were accepting an error. It was not completely the same.
More questions? No? Just one comment. On your, one of the first slides, you mentioned that there were a data gap 2015. And I think that it was my fault actually at the time.
I know. I think from up to Milan to Italy, there are data.
I think
the
that
frame after that is missed.
At the time, we were having a lot of problems with radiometric calibration, and our transponders were located in Germany close to DLR. So we need to acquire diversity of modes and polarizations that create the gap that you are probably actually seeing.
I mean, I think it's normal when a mission is starting, so we are we were not complaining.
So is there any more questions for Julia? Yes.
When analyzing such extreme topography or some terrain like in Switzerland, you learn a lot about problems in your processing because they show up in this terrain. So did you learn anything for the rest of Europe to better process this data?
Oh. I mean, okay, Alps are covering already a big part of Europe, so I think some challenges are there. Oh, I mean, I now present this. We used to work all over the world, so it's not that we just work over Switzerland over here. So for sure, one other issue that is, again, a big discussion, recent discussion with moisture over fields. So this is another big topic that is here, but everywhere in Europe for sure. Then, yeah, I can go through many problems. So every time I process data, there is something that should be considered. So at the same time, I think it depends from the accuracy you want to get. There are some errors that you can tolerate, like atmosphere. I mean, every time you need to tune atmospheric artifacts, depending where you're working on. Sometimes it's not an issue at all. Sometimes, depending on the sensor you're using, is changing the issue. So it's still not something that is fully solved, but depends on the scale of displacement you're analyzing. If the artifact is bigger than displacement, then you need to somehow take care of what is going on.
Questions?
So if there is no more questions, I'd like to thank all the speakers and the audience for this session and for all the good questions. Thank you very much. We have the coffee break now, and we restart in 30 minutes or 40 minutes from now. Thank you very much.
Yeah, thank you.